everybody. Welcome to the Western Region Colloquium. Today, it is my pleasure to introduce our speaker, Ripudaman Malhotra. Dr. Malhotra is an Associate Director of the Chemical Science and Technology Laboratory in SRI's Physical Sciences Division. He is an organic chemist, and during his tenure at SRI has worked extensively, though not exclusively, in the areas of energy. Most of his studies have focused on the chemistry of processing fossil fuels. His detailed mechanistic studies of these systems have resulted in innovative processes that achieve desired product selectivity and increased efficiency. As someone deeply engaged in energy research, he was acutely aware of the looming energy crisis, which was being exacerbated by the potential of global climate change. His broadened research interests into studying alternate resources such as biomass and application of biotechnology in the areas of energy, chemicals, and the environment. In 2005, he joined Hewitt Crane and Ed Kinderman to co-author A Cubic Mile of Oil, the Looming Energy Crisis and Options for Averting It, which was published by the Oxford University Press in 2010. He has spoken extensively on the subject of various technical and business fora. Among his technical works are over 90 papers in archival literature, co-authorship of a book on nitrations, the editing of a book on combinatorial materials development, and co-editorship of a book on advanced materials. He is the section editor for a soon-to-be-published Encyclopedia of Sustainable Science and Technology, and an active member of the Petroleum and Fuels Chemistry divisions of the American Chemical Society. In 2005, he was named an SRI Fellow, the highest award SRI bestows on its employees for excellence in research. And there are a few handouts that Dr. Malhotra brought on the table back there summarizing what he's going to be speaking about today.
Thank you very much, Darcy, for the kind introduction. And thank you all for coming and giving me this opportunity to speak on a subject that's so near and dear to my heart. And I really liked talking about it. But talking to this audience seems a little bit strange because all the information comes from USGS, most of the information that I'll be talking about and that my co-authors and I wrote in this book, A Cubic Mile of Oil. A lot of it comes from the work done here at the USGS, so it seems like preaching to the choir. Anyhow, the topic of the presentation, the title, A Cubic Mile of Oil, comes from the fact that our current consumption rate, global consumption rate of petroleum, which is about 80 million barrels a day, adds up over 1 year to a volume that's just about 1 cubic mile. And we thought that it would be good to use that as a metric to describe energy from all different sources in the same way. And many of us were quite aware of the energy crisis back in the 70s. And somehow we thought that we were moving along, and then we lost momentum. It was difficult to sustain the conversation. And I think the public pressure is needed to be sustained over a long time. It's a large enterprise. It takes many, many years to effect real changes. And to be able to sustain a conversation about it is challenging. And part of that problem was lack of language. And although the information that I'm presenting here is not going to be new, I think the language may be a little bit new. And it may help us all as we go out in our daily lives and talk to our friends and colleagues and children and grandchildren, that we can perhaps spark some interest in the curiosity to continue with this work, and that realize that that there are lots of tough choices ahead. And that's what we will be we need to be debating and letting our desires and our wishes known, so that in a democratic way we can affect the changes that we desire. So let me begin by this. It already said that the energy challenge that we face is probably one of the toughest challenges ahead. And it's actually time to reframe the debate about global energy supply. Oftentimes, the energy supply has been portrayed as a tension between, on the one hand, to protect the environment because our current practices of using energy and producing energy are unsustainable, against the economic interests of the energy industry. If it is portrayed in that manner, the choice is fairly simple. We have to protect the environment. But the reason there is doubt or there is some hesitancy on the other part is you realize how vital energy is for everything that we do. And it's not just the economic interests, but it's also a moral imperative to provide energy so that people can live healthy, sustainable, productive lives. So it's balancing one moral imperative against the other that causes us to face the bigger challenge. So yes, the current practices of energy production and consumption are unsustainable. Yes, the energy use is central to the way of our life, and consequences for not meeting it are very dire. This tension is what we will be talking about a little bit, and we need to maintain that perspective as we look for solutions. But of course, we need to begin by acknowledging at least the magnitude of the problem. So we have to ask questions like, well, how much energy do we use? What do we use it for? Where does it come from? Simple questions like that, but in understandable, relatable manner. And that's what the next half an hour or so I think I'll be covering. So how much energy do we use? Now, it's a good question, but immediately we are confronted with this Tower of Babel. We use different units to express energy derived from different sources. We always talk about gallons or barrels of oil, or metric ton equivalents, tons or BTUs for coal, SCUFs, which is standard cubic feet for natural gas, kilowatt hours for electrical energy. And the lack of uniform units makes a serious impediment in the path of a meaningful discussion. Further creation of confusion arises from the fact that each of these units, gallons, barrels, tons, SCUFs, represents a fairly small amount of energy when talking about the global flows or national levels. We are required to use multipliers like millions, billions, trillions, quadrillions, what have you, and these are really mind-numbing. I don't have to give you examples. I'm sure you all have seen, as I have in the media, and people stumbling over it, even energy experts. I heard CEO of one of the major oil companies in talking mix up billions and trillions, and it's very common. I slip on them all the time myself, and I've been working in this field for 30 years. So my colleague Hugh Crane, while he was waiting in the line in the 1970s, came up with this realization of that the global oil consumption at that time was approaching 1 cubic mile. It wasn't there, it was quite less. But he started thinking, how much oil does the world consume? And Hugh was very good with kind of picturing numbers and all that. So he started estimating, because the line was long, he had a slide rule, he pulled it out, he moved back and forth a few things, and how many cars and how much, etc. And he came up with 700 billion barrels or gallons of oil. Well, how large a pool is that? So a few more slide rule strokes, and said, oh, this is about 2/3 or somewhere between 2/3 and 3/4 of a cubic mile. So then he approached Ed Kinderman, and who was leading the energy center over there. Many of you may know of these two gentlemen. And they started working on the book, this cubic mile of oil, which I heard a lot. And a few years ago, I finally joined them. I said, well, let's just get this book out. I think it's time. And, so here's I tried to visualize this, and I wanted to put a common monument or something over there to the side to get the scale. But you see there's a Statue of Liberty and a red circle around it. The red circle is there to remind me that that's a magnifying glass, a very powerful magnifying glass, because a mile by mile by mile, just you wouldn't see the Statue of Liberty and that. Let's think of another, where did that go? So I'm missing a slide here. We've all been to some large stadia. Picture one, which is say about 600 yards across and about 20 stories high, like the Stanford Stadium not far from here. That cylinder, if you were to fill it up, would be about 1,000th of a cubic mile of oil. So 1,000 such stadia would make 1 cubic mile of oil, or 1 cubic mile. It is a very large unit of energy, if you look at it that way. It is about 26 billion barrels of oil, where billion is 10 to the 9. When I was growing up, a billion was 10 to the 12, or where I was growing up. That's how we used to. So it was a confusion. It was another source of confusion. And that's about the current worldwide oil consumption. Abbreviated as CMO, you may hear me slip to that instead of saying cubic mile of oil every time. Now, 1 CMO is equal to 153 quadrillion BTUs, and that's about 6.5 billion tons of hard coal, or 15.3 trillion kilowatt hours of electricity. And many of you may notice right away over there that I am discounting electricity in a different way. I'm using a heat rate of 10,000 BTU per kilowatt hour, not the 3,412 BTU per kilowatt hour that's in the textbooks. That's because most of if I have a source of energy that gives me electricity directly, then if I use that source, I have already displaced not just 3,000, but more like 10,000 BTUs. So if I'm displacing that much oil, let me use 10,000 BTU per kilowatt hour. So that's why when we're talking about alternate sources like wind or photovoltaics, which give you directly electricity, and you may want to discount the fact that they are giving it you directly into something that's desirable, and use a heat rate equivalent for how much oil they would have displaced. When I talk about with friends, and even those of us in the physics community sometimes, how much is a BTU? And we don't have much experience with that directly. Well, actually, a BTU is the energy from a simple burning match. Fortunately, we don't, many of us have not smoked or don't smoke and don't use matches like that anymore, and that's good. The other thing that we use a lot is electricity, and I wanted to get a feel for how much is a kilowatt hour also. Now, I'm not an athlete, but I do get on the gym sometimes and work on a exercycle. And my exercycle has a little meter. It shows me how much electricity I'm producing. And 100 watts or 110 watts is fairly easy for me to maintain. But even to push it up to 125 gets very, very difficult. And at 125 watts, I'm really sweating profusely. Now, it would take me 8 hours working at that very fast speed, 125 watts, to produce 1 kilowatt hour of electricity. Now, that's the amount of energy in a day's work that my utilities will sell it to me for less than 12 cents. Am I willing to live for that, 12 cents for the day's work? Probably not. And the energy that I derive from that 8 hours workout is of only about 1/10 of a gallon of oil at the discounted rate. Here it is, visualizing. I'm sorry, it's got out of place. So 1,000 such stadia, that volume would be what's a cubic mile. So let's come back to the question, how much are we using of the different sources of energy? And we already said, well, from oil we get about 1 cubic mile of oil. From coal, the world derives in equivalent, it's 0.8 CMO of energy, about 6/10 CMO from natural gas, and close to 2/10 each from nuclear, biomass, and hydroelectric. And the biomass is basically wood burning. This is not biofuels. That's very little at the moment. So between 1, 0.8, 0.6, and comes to about 3 CMO per year. That's the current rate of energy consumption. Geothermal, wind, photovoltaic, solar thermal, and all right now barely register on this scale. This is what we are, that would come from, comprise our income sources that we are deriving every year. What we are living off right now are, if I get my point, is all our inheritance. This is what we inherited: oil, coal, natural gas, and the nuclear materials. More than 85% of the energy is what we are using, is we're living off our inheritance. The question is, how long will it last? Now, the second question that we often ask is, well, okay, so that's what do you use your energy for? So if you look at the total primary energy from all the sources, the 3 CMO that are coming in, you see that more than a third of that primary energy goes right away into making electricity, and we lose 2/3 of it right away because heat rate for electricity production is about a third. And the remaining is divided into either commercial residential, that's just what's used in the buildings for heating, lighting, ventilation, transportation, and all different industrial uses. If we take the amount of energy that was used in the electricity generation and apportion it to the different sectors that ultimately use that electricity, the picture changes a little bit, and we find that there are 3 different sources, sectors that are using about equal amount of energy, about 30% each. 29% for transportation, 32% for industrial, and a little more commercial, residential. The buildings, what's used in the buildings, in the making and maintaining of the buildings is the largest one, 39% of the energy going into that. So who's producing it and who's consuming it? Here's another way of looking at it. We take the information that USGS and many other bodies in the world have given us for the assessments of the production of energy from all different sources, primarily oil, gas, coal, nuclear power, and hydropower, because these are the ones that are really mattering at the moment, and divided the world into the 7 regions: North America, Central South America, Europe, Russia group, Asia Pacific, Middle East, North Africa, and Sub-Saharan Africa. And then we, for each of these regions, there are 2 bars. The first one is the production, the second one is the consumption. And there's further detail in terms of how much of each of those sources. If you look at this, what surprised me when I did that was, North America produces more energy than Middle East, North Africa region. That was a surprise to me. It wasn't a surprise that lasted very long, but yes, it was. Initially, it did surprise me. As did it surprise me to know that even Asia-Pacific region has a lot more energy production at the moment than Middle East, North Africa. It's just that these 2 regions, the North American and the Asia-Pacific region, they may produce a lot, but they consume in even larger amount. And that's why these are the 2, along with Europe, the major importers of energy. And as we look at different sources of energy that are being exported or imported from regions, we can see the source of the political tensions that can arise from those also. Another way to look at the consumption is to look at it not on the national level, but on at the per capita basis. So here again, the 7 bars over here, but they're displayed somewhat differently. The height of each of these bars is the per capita energy consumption. And a cubic mile of oil in the case of per capita consumption would be just as bad as using gallons to describe global flows. We reverted over here to gallons of oil equivalent of energy when we're talking about per capita. So per capita energy consumption in North America is about 1,800 gallons of oil per year. The width of each of these bars relates to the population in that region, so that the area, which is the product of the two, will be the total consumption of that area. So this is the 0.7 CMO of consumption in North America region that we saw in the previous graph. I keep losing my pointer. The global average line is here in the middle. It's about 450 gallons of oil per year. Europe's around 900. The Russia group's a little more than 1,000. And then there's a very broad line here. This is the Asia-Pacific region with more than 3 billion people, which is barely 250 gallons of oil per year. Even lower is the Sub-Saharan Africa, a fairly broad, also, you know, half a billion people over there. See, I slipped on millions and billions. So if we were to allow the people in, say, one region, let's say Asia-Pacific region, to improve their standard of living and arrive to a level equal to what the global average is today, which is about 450 gallons of oil, how much energy do we need more? Then we'll need another 0.7 CMO of energy. That's the entire energy consumption of the North America region. So even if the entire North America region were to go all the way down to zero and not consume anything, you could barely make up for the growth over there. It kind of immediately shows you the limitations that we have of efficiency gains and conservations. They are important. I don't want to say that they are not important, but they alone cannot be enough, is the point. And if we were to continue with the growth over there and take it to the half the North America standard of living, of course, in the energy consumption, let's say, which would be comparable to the European group level, the additional energy requirement would be a 1.5 CMO. And all this is without changing the population anymore. If there's further population growth, that's a different matter. That would increase the energy consumptions even more. So let's look at the projections for the future. These are just scenarios. These are not predictions. I do not want to predict what the future energy consumptions might be, but these are the trends that we see. If we follow the traditional energy growth curve for the last 50 years that's been going on, that's been 2.6% per year. That's the level at which energy growth has taken place since the middle of last century. If we follow that red line, by the middle of this century, we are above 9 CMO per year. If we follow somehow, let's say, a 1.8%, which is considerably lower energy growth rate, that would put us around 6 point some by the time of the middle of the century. And if we follow the growth rate of about 0.8 CMO, that's even 0.8% per year, which is really hardship actually in many parts. That this really causes economic consternations. That puts us at about 4 CMO per year. Now remember that we could think, well, there are ways to conserve and improve the efficiency so that we may not want to, we may not have to follow the line of 2.6%, and that's true. Except, remember, the 2.6% number comes from the fact, is the growth rate from the last 50 years, out of which at least 30 plus years have been when the world has been practicing fairly good energy efficiency measures. It may not be all the way enough. There's plenty of room for improvement, but we have been. It's not willy-nilly using energy unwisely all the time. So even with that one, so that much efficiency gains have already been included. All those Energy Star appliances and the better heating systems and all that, they're already included in this 2.6% growth rate. And as we saw in the previous slide, the drivers for increasing energy consumption, which is the standard of living and the population, they're already there. They're already built in. So I see very difficult to to imagine a scenario when the global energy consumption in future would be less. But let's say even if it were, let's say we follow this green profile, that we allow for some growth to follow the red line for a while, and then we manage somehow to turn it around. The question that I wanted to ask was, well, how many CMOs have I burnt under each of these cases in the next 50 years? And the answers are here. Now the numbers are really staggering. Anywhere between 160 CMO to 270 CMO of energy. That's a very large amount of energy. Do we even have fossil reserves or resources that will cover that? That's a real question that I have to ask. Now, this slide is for the benefit of not USGS, the non-USGS, also for you to be able to communicate to the people. Yes, for the last 60 plus years, we have been hearing that our petroleum reserves will last us only 40 years at the current rate of consumption. Our current rate of consumption has kept increasing over the last 60 years, and we still have another 40 years of petroleum reserves. And you know the answer to that, so I won't bother you with that. But we need to explain why is it that what's defined as reserves is something like what you have in the bank already, and it's what you can derive with today's technology at today's prices economically. And once you have reserves of more than 40 years, there is no incentive for anybody to invest another dime looking for more of that resource and converting it into a reserve basis. So below the reserves we have these resources, and first they are the conventional ones, and then we have even larger amounts of unconventional resources, and technology keeps developing. Nevertheless, let's see how much do we have if I add them all up. Because in the previous slide we saw numbers that were in the hundreds of CMO. So here are the numbers. The oil reserves, the global oil reserves right now are standard at about 46 CMO. Gas reserves stand at about 42 CMO. We have additionally 94 CMO of resources for oil, the 66 CMO for natural gas. Well, that's only 140 for oil and about 108 for natural gas. That's not a lot. We were seeing 170 to 270 in the previous graphs. We do have coal. In the reserves we have about 120 CMO. Well, that would take away pretty much all the coal reserves. We do have 1,500 CMO under there, but these resources that we are talking about, the additional, they do require more energy input. So since these estimates refer to the hydrocarbons underground in place, not necessarily how much you can extract or remove and how much energy it takes to withdraw them. The amount of energy that we can derive from them is still limited. And the interesting thing about exponential growth is that no matter how large this resource, we will just run out of it. If we can, even if I can run out of 1,000 CMO of total energy in another 150 years if we continue on any of those exponential curve growths. Plus, the continued use of these resources will increase the CO2 levels in the atmosphere, and that's something to be worried about too. I don't mean to discount that we need these sources. I think it's time to look for alternate ways to switch to our energy income sources instead of the inheritance, the renewables. Fortunately, the global energy mix changes have occurred in the past. It's not the first time we are confronting this. But there are some things that we can learn from these, looking at the graphs of how global energy mix changes over time. And by and large, you see that it takes a lot of time, lots of decades, 5, 6 decades or so, before any new resource begins to make a dent and come alive into the market. For example, we had more than 80% of the energy was all from wood biomass burning. Coal was discovered back then, but it took coal good 50, 40, 90 years to become equal to what the wood burning was. And then you can see that whereas the oil was discovered back also in the early 1840 was when it was really discovered, 1846 or so. But it doesn't rise above the baseline here till the latter half of the 19th century, till the very tail end of the 19th century. And look how long it takes, almost 70, 80 years before it equals to that of wood burning. Coal burning is 1960s when it surpasses that. It equals the wood burning in about 20, 40, 50 years or so before it equals the wood burning. There are times when other interests like the military advantages, etc., can help the development of some technologies, as it happened for oil and also for nuclear. And that tells us that there are ways sometimes we can increase the speed with which these things can be developed, but not necessarily. It does take a very long time, and I thank Jim Margulies for this cartoon that he had drawn many, many years ago. No, not too long ago, just 4 years ago. But drawing on the fact that going back so many presidencies we have been talking about, we need to make the change, we've got to get oil independence and things like that. So why does it take so long to scale? And there are many roadblocks along the way. The expansion is slowed down by, first of all, the sheer inertia of the incumbent system. It's really huge. The market acceptability. This is a very large thing. You cannot change the price of electricity or energy without affecting the price of everything. There are sometimes new infrastructure requirements as you introduce a new energy source into the market. Lack of trained personnel. And of course there are attitudinal things also, which is like the NIMBY, which many of us have heard of, which is not in my backyard. But now increasingly we hear about NOPE, which is not on planet Earth, or banana, which is built absolutely nothing anywhere near anything. These things slow down the development. And we have seen historically that yes, we can have more rapid penetration of new technology if it affords some strategic importance to the military, or if there are some real values that the market sees it. If you can produce something enabling the new technology, really enables the way people are doing business or something, it can catch on, it can add value, and therefore it will be appreciated. So now we start looking at, after this, let's look at our different options that we have for, first of all, this is nuclear is another of the inheritance, but it is one non-CO2 producing source that is somewhat at scale at the moment, whereas the others are even lower. And we see that, well, it's an established scalable technology. It has a low environmental footprint, and yes, there are ample amount of reserves available at the moment. But it is confronted by a huge lot of risks. There are lots of, the risks come under three different flavors. First of all, which is really the most important one right now, are fear. It's not a real risk. It's really fears about radiation exposure and fears about a nuclear explosion. And I think we as a scientists, as a group, really have not done a very good job of communicating that the public concern in this area, these areas are really fear-based. It's not a real. Now there are some technical challenges also, and there are some political ones, and they have to be confronted as well. But anyhow, I will come back to these if there are questions, otherwise it may be staying too long. But we go through the different options that we have, and let's continue on. So, and of course then there is the nuclear fusion. If it's realized, that would ameliorate a lot of these risks. And there are some other nuclear cycles that people have been talking about, like the thorium cycle, which I believe seems to have a lot of promise if we can work with the breeder technologies, but we won't learn unless we do them. Now let's contrast that to our energy income sources, and let's look at what the sun offers us every year. It's 23,000 CMO per year, and we are looking for what? 3 CMO, 2 CMO, 4 CMO, that's all? What's our excuse? This is the source that we have to get to somehow or the other. It may take us a little while, and we can use the endowments that we have in the interim, but ultimately we have to get there. But that's not easy also. It's more easily said than done. We see the end goal over there, but how do we get there? There are lots of considerations that we have to look at along the way. First of all, if there is another income source, we have to first of all ask, does this source scale to the CMO level? Does it have the potential to supply that kind of at that level? Will it require new infrastructure? Because you better include those costs as well. And is this new infrastructure directly applicable within? Nuclear had a great power because its product fed right into the structure that was there, the electrical grid. When people talk about the hydrogen economy, it's going to be a little difficult because it requires a complete new infrastructure for transport and delivery of hydrogen. What about its environmental footprint? What's its energy return on the energy invested? And let's not look at total energy invested, but let's just look at the fossil energy that needs to be invested. Many of the practices in biofuels production answer part of the things. They make it possible to produce some total energy, but they also consume a fair amount of fossil energy for their production in terms of the fertilizers and other inputs that are required. Sure, they convert it's a way to liquefy your coal and natural gas through the use of plants, is what it looks like to me. Are there competing land use issues? Are there competing water use issues? And at what price does it produce? These are all considerations whenever we are looking at a difference for a new source. Let's look at some examples here in the next couple of slides. If you look at direct solar, what are the challenges? And I'm not going to pretend that I have answers. I don't. I'm just posing some questions here. But we have to confront the realities. The cost of PV is about, unfortunately, right now about 35 cents per kilowatt hour, many times more than producing from the current practice from nuclear even, or coal or oil. It's not much from oil, from natural gas and coal. The intermittency reduces its availability to about 20% only. And so that means that you need about 4 to 5 times the larger installed capacity. So yes, I give you the better discount rate that it gives you, every time you produce a kilowatt hour of electricity from photovoltaics, you have displaced 10,000 BTUs worth of oil or coal, but you do need, for installed capacity, it's not that a gigawatt of PV is equal to a gigawatt of nuclear or a gigawatt of coal. There are some issues around location. If we think about photovoltaics on rooftops and offices, they are close enough. That's good. But then we see that they are not, the area available is not sufficient to provide for the entire system. If you consider utility scale systems, then you can take advantage of the fact that you're averaging over a large number of users, and so overall installed capacity may be required maybe a little less. But these things then tend to be remote from population centers, and electric transmission lines, etc., that are needed from the new locations do run into some NIMBY type issues and problems a lot. Wind power, another one that runs up against NIMBY all the time, has a lot of pluses. It has a huge potential. You can produce many CMOs per year. It's a relatively low cost one also. On the negative side, we have that it's really intermittent. Wind is fickle. You have only about 25 to 30%, and therefore you need either some kind of a backup power production with the natural gas or a lot of storage systems. It's very dilute. It's about 8 to 10 megawatts capacity is all that you can get per square mile. And so that relates to the question as well, whose land are you covering or whose habitat are you interfering with? And oftentimes the desired sites are all very remote from the consuming centers, and which again brings up the questions of transmission of energy to the consumers. Look at biomass and things like that. There's certainly a lot of hope and hype around it. It is one source, renewable source, that produces a storable fuel, unlike photovoltaic and wind that produce electricity which don't have a way to store. But many of the practices are currently, they don't necessarily reduce greenhouse gases, particularly when you account for the indirect land use change effects that come into play. They do constrain a lot of water supplies, and they disrupt food supply issues that are leading to food riots and things. So these are the concerns that one has to balance against the fact that here's a renewable source that has a potential to supply at least about half a CMO per year of energy. Well, let's look at on the side for the demand side of things, which is let's look at the buildings and all, and are there ways that we can reduce the consumption? As I said, buildings do consume about 51% of the primary energy. 39% is used in the operations. That is for the heating, ventilation, air conditioning, lighting, appliances, and things like that. And about 12% is used in the materials production that's needed for the buildings in terms of steel, concrete, glass, sheetrock, you have it. Energy saving practices can pay off. Better insulation, heat lighting, efficient lighting and efficient heating are all very good things, and if we can implement them and slow down the demand curve, it can help considerably. And of course, the smart grid would also allow for additional ways to make better use of the resources that we have. So how much energy do we look at? Well, the opportunity in the US or in much of the developed world comes down to, when you add up, about 1/10 of a CMO per year. That's not a whole lot. There's a much bigger opportunity for these materials and all that practices with a potential impact of about 2 CMO per year, but that's if only you can, that's in places like India and China, where there's a lot of construction going on and there's a lot of development, new development, because in the already developed countries, the penetration and all will depend only on when buildings turn over. But in the developing, where they are really building basically the entire US over the next few years, there's plenty of opportunity. But the big challenge would there be, are these new green materials and the green practices, are they cost effective? Can it meet, as Vinod Khosla talks about, the Chindia price point? That's the challenge. Efficiency and conservation, well, so we'd like to distinguish a little bit between the two. Efficiency is using less energy to do what we already do, and we continue to do that. It's the easiest and most economical path. It doesn't require much sacrificing. You just, okay, I've got light, and I'm going to have a more efficient light, and I'm going to use the light. But I'm going to use less electricity. The problem is that this efficiency pathway historically ends up increasing the total amount of energy. It has never really reduced the total consumption of energy. Our refrigerators today are remarkably more efficient than the refrigerators of the 70s. Well, they're just bigger. The TVs today are many, many times more efficient than those big CRT tubes. But we have many more TVs, and we have many more square inches that we view. That's a matter of fact. That's what happens. Conservation would be like avoiding what we needed to do in the past. If we change our lifestyle, this has potentially a much bigger impact, but it's tougher to implement. It requires switching to things like high-density urban living and mass transit. That would be wonderful for the total energy consumption we could reduce that. You know, when we talked about the energy consumption, how do we use it, and we talked about transportation, industrial uses, and what was it? The built environment was one, industrial sector was the other one, and transportation was the third one. Those three main things. What was missing in that was the food. There was no slice, no place for food. Or where is food? Food's everywhere, actually, because a good part of the food is in the industrial section. A good part of the food energy is in the transportation, and it's also in the built environment. It gets rolled into. It's never displayed separately. And some agencies have done the work, and they've looked at it, and it really comes out as a surprise as how large is the energy investment that the world makes today for food. Almost 20–25% of primary energy goes into that. If you look at the greenhouse gas impact, it's even larger. So switching or making adjustments in your diet can have a huge impact, much more than what changing light bulbs would do, I submit. We have some numbers and examples, and I'll be happy to go over them with some others later. But let me come back to the big question that we had. Well, what does it take to produce, say, 1 CMO per year from various sources? And it is an enormous task requiring trillions of dollars. If you look at large hydro as an example, I'm using the example of the world's largest system, like the Three Gorges Dam. How many do we need? We need about 200 of those. Now, there aren't that many rivers that could sustain that, but okay, let's say if we wanted to build 200 of Three Gorges Dams kind of facilities, we need to be commissioning one every quarter for the next 50 years, so that we have 4 a year and 250 years. If we want to build nuclear power plants, say a 900 megawatt facility with 90% availability, then basically what it requires us to do is turn one on every Monday from now to 2060, for the next 50 years. Then we'll have enough nuclear power plants that will give us 1 CMO per year worth of electricity. If we want to go with consider solar power, now the biggest solar power plants are only in the order of a couple hundred, 150 or so megawatts. But let's imagine we do a really bang-up job and we can make a much bigger one, something like a 900 megawatt, the same size as the nuclear example that I was using. Because the availability of the solar facility is going to be somewhat less, we need more. So instead of starting a new nuclear power, a new facility every Monday, we now need to start a new facility every Monday, Wednesday, and Friday. You want to do windmills? You need about 3 million of those. This is using the example of a very common 1.65 megawatt Vestas system. You need about 1,200 a week for 50 years. 1,200 a week doesn't seem like a lot, because a windmill is what? It's something like a large bus, if you will, sitting on top of a pole. That's the transmission system. That's certainly doable, but what we run up against is, where are you going to put them? Offshore seems to be a possibility. Well, for one thing, they are also, a lot of the world's population really lives near the coastlines. So offshores, say a few 10 miles or so out, also reduces the problem that you have for transmission. But servicing them, etc., is going to remain a big challenge, and we don't know what the costs are, but I think we won't know it unless we do it. And if you want to go with the solar rooftop systems, I take an example of a 2.1 kilowatt system that I could find commercially. We need about 250,000 of them, 250,000 every day for the next 50 years. So what's the path forward? Well, indeed, we can see that our current solutions are woefully inadequate to really to address the need that we have in the future. Innovation is needed on all fronts to meet the energy demand. Reducing the demand from the projected 9 CMO per year to 6 CMO per year itself is going to be a major international effort. It will require many, many new technologies and new ways of doing business. Our planning cycles therefore need to last for 40 or more years and not 4. And they have to consider the fact that they have to transcend the prevailing price of oil. The price of oil has been often taken as the measure of energy across because it does affect everything, but it goes up and down a lot. And it's really the marginal price of oil that we see, not the total. And that is a leverage, that's a real hurdle that the banks and people who are controlling the money will have to watch that. But we have to, if we are making a policy, we have to go beyond that somehow, or else we will never be able to get our feet off the ground. We do need a family of innovations. We need things for the short term, some for the intermediate term, some for the long term. In the short term, of course, there's the conservation and efficiency, perhaps concentrated solar power, nuclear, and most important, something that has to be done right away is public education. In the intermediate term, I believe that we will have much more of unconventional hydrocarbons, new engine designs that are much more efficient. Our current engines deliver about a third or so of the energy from the fuel to the motive power, or even less in many cases. And there are many, I'm heartened by the developments that I'm seeing in this arena. There's plenty of headroom and there's plenty of improvements. Actually, over the past 40, 50 years also, since there was the past 40 years, since the first things, the cafes were installed, the engine portion has improved its efficiency considerably and has continued to be, even though it's not reflected in the fuel efficiency of the cars. The engine produces enough energy, motive power and other things to service many other things, such as the performance of the car and many other systems. So that has continued to develop. We will see some biofuels and, of course, the electrification of the transportation sector by having electric vehicles and things like that would also make an impact. That would, of course, not necessarily reduce the energy consumption. It just switches one fuel for another. And on the longer term, I see thin film photovoltaics and perhaps nuclear fusion coming in. And given all the things that we've talked about, what it takes to produce even one CMO, and our needs are going to be in 5 or 6 CMOs that we are looking for, I think it's not a question of either or, it's a question of and. To make an impact, we will need all the technology options. We will need efficiency and conservation and nuclear and wind and solar and whatever. So I leave you with this quote from the French Marshal Lauty. It's urgent because we are late. He asked his gardener once to plant a tree. The gardener objected that the tree was slow growing and would not reach maturity for 100 years. The marshal replied, in that case, there's no time to lose. Plant one this afternoon. So let me thank you for your attention, and I'll be happy to take some questions.
You didn't happen to mention tidal sources of energy in which you can, Eastern Canada probably has that, and most of the population lives near coastlines anyhow, and to use the wave action of the water to convert energy. Maybe that's minuscule compared to what you're talking about.
Yes, I didn't mention that. We do talk about it in the book, and there are two things that you mentioned. One is the tidal, and the other is the wave power. Their origins are different. And yes, at the moment, the tidal power does seem to have, in some areas, a fair amount of potential. It doesn't scale to a CMO level. And of course, whenever they have tried to do that work near Britain, around that part, they have run up against the problems with, it disrupts the fish flow, it disrupts also the other things, and that was one of the reasons. In terms of wave power, I think the technology is being developed. There's still a long ways to go. It takes tons and tons of material to really, even if it is steel, it doesn't matter what it is, but it takes so much stuff to produce a kilowatt hour, produce a power capacity for 1 kilowatt, that I see no way around that. The energy that you would invest in the materials, it will take you a long time to pay back for that, for the systems. And then you are out in the ocean. It does serve a very good purpose in providing energy for buoys or for other navigational systems or instruments that are monitoring things in the ocean. That certainly does. But if I want to draw that energy back to the land where people are going to use, I see a mismatch at the moment of the technologies in terms of the stuff that is needed to harness that wave power. Yes, ma'am.
Can you wait for the microphone, please?
Have you looked at all at how much energy it takes to recycle these industrial complexes that generate electricity? Because they have a lifetime, and when you recycle them, they would, I assume, use energy.
Not as detailed as I would have liked to have. We did not do that. That analysis is not in this book. But we do look at emissions on a life cycle basis. Yes, that part was done. But many of these facilities do require energy investments to put them up in the first place, and unless they have a life of so many years, they don't even pay for that. Dams, for example, are one example. We can look at that, and we discussed that. You can see that the cement and all that went into, and concrete and steel that went into their production, they can pay for themselves in a fairly short order. It's not that many years. But what I don't know, where things get really murky, is the emissions that are associated with the land that got covered. And because it got covered, then there's anaerobic digestion now going on of the plant material that was behind them. The estimates for that get very, very difficult to assess. But the direct material costs were fairly easy, and the emissions associated with that were fairly easy to document. And you can see that, yes, the dams can produce a fair amount of energy, far in excess of what it takes to build them.
Thank you. Interesting talk. One thing you didn't mention there at the end is what are the impacts for this scenario on climate change or production of CO2?
Yeah, so it's a matter of choice, really. We have to consider, and I don't know how fast we have to consider it, but I know if we turn our current systems off, we are depriving many people the opportunity to get out of poverty and out of subsistence level of existence. And then the second part of that is we have to think about, okay, we are willing to do certain things, but are we sure that we are really having the impact? What is it that we are really trying to affect? Is it the CO2 levels? Is that what it is? How sure we are of that? And by doing this action, are we really making an impact? Because it's global. And so you can turn off your side, and there will be the impact on that. But if someone else, whatever you can save, is outweighed elsewhere, then you haven't achieved anything. So it's those questions that are at the heart of it. But that's not to say that there's no reason to waste any. We don't have that luxury anymore. And I think there are choices here. If the objective is clear as to what we are trying to achieve, if the objective is I want liquid fuels and I don't care about others, there are some solutions. If you say I want to cut my CO2, then let's look at what things are. One example I gave you was if we can choose to live in smaller dwellings, it'll make a huge impact. If we switch to public transportation, it'll make an impact. If we change our diet, it'll make an impact on CO2 a whole lot more. than by doing some of the other things.
I actually think that you covered everything very nicely. Somewhat related to the last question, if we could also attach a total cost to every energy source, whether it's coal, and if we can include whatever water requirements are,
Yes.
whatever CO2 emissions are, if we go nuclear, then the security issues and others.
Yeah.
If we could add those things up, rather than just say, well, the cost of solar is 2 or 3 times more. It would be nice to do that.
Absolutely.
Without that, would you say that the cost is comparable now? I mean, we go with the cost, basically. I mean, coal would be cheaper for generating electricity, nuclear also in some other areas, and so on. So where does the total cost versus
Total cost.
now cost?
Yeah. No, it's a fair question, and we do discuss that in the book. I didn't talk about it today I wanted to limit my comments as such. It took me a lot longer to cover. I thought my talk was going to be shorter than that. I thought I would be finishing before 4 o'clock. Well before, but it took me almost to leave you enough time. And then, the cost is how much cost do you, and do you discount those costs also? Because when you look at that, look at the cost of action versus inaction, and I'm not an economist, and when I read the Stern report, I thought, okay, it's very clear, it's a slam dunk. We need to do everything we can to reduce the CO2, otherwise the cost of not doing something is so many times more than for the cost of action. But then we looked at the cost of not doing anything by Nordhaus and others, and looked at the analysis and said, well, Stern has deliberately not taken any future, the net present value of those. He has his reasons. That's not the accounting practice that you and I like to, live under. Whenever we borrow something, we have to pay an interest. And those things. So it left me a little wondering what cost will we use. What's the cost of keeping those lanes open? The oil price may be $100 a barrel or $150 a barrel. The cost of finding and lifting the oil is nowhere near that. That varies from place to place, maybe sometimes very little, in some places a little bit more. But we all end up paying the marginal cost of oil that is there. For coal, what's the cost of all the associated diseases that their use entails? It's a lot. But then again, if you're burning wood and you switch that from wood to coal or burned electricity, which then comes to homes, you can see it makes it improves the health of people a whole lot. So switching from wood to coal I have seen it happen, improving the lives of people. It's not just worsening their lives, it was really a value that was being added, because they're not smoking inhaling the wood smoke, but now they have something else that burns inside. There are some other options also that we talk a little bit about and didn't get a chance to talk here, is since our concern is it is global, and the solutions that may not scale here may scale quite adequately elsewhere. And the point is that the growth sectors is the growing need of energy to improve the living conditions is not here, it's elsewhere. So there could be windmills and wind power things where you don't have to worry too much about building exotic backup systems, because your backup system may be nothing more than just having pumped the water and save half the population from worrying about spending all their lives just fetching water. You made a huge impact on the lives of the people over there by having small amounts of even small amount of photovoltaic systems or things, which is not available all the time. But if it allows them to leapfrog and be able to participate in the local economy, because now they can use their cell phones, which they can charge. I was very pleased to read the story, and that's how they even trade and buy and sell their goods, because it's all being done through the cell phone. changes their lives. It makes a much better impact on them. So this technology may not be good for somewhere where they are using, say, 2,000 gallons of oil per day, per year per capita, but may be quite adequate and quite game-changing for other places.
As we go to more unconventional and hard-to-get fossil fuel sources, do the capital costs increase to such a level that it gets harder to even consider investment in some of these alternative energy sources? What's the trade-off there?
Yes. Capital costs are the major impediment at the moment. But if the real price of oil that, is at $100 a barrel, there are many more technologies that are accessible to you. You could convert gas to liquids, you could convert coal to liquids. But if I were to go to a bank and say, well, give me a loan because I'm going to do a coal to liquids, and look, I can produce coal to liquids from at, say, $35, $40 a barrel, and I can sell it for 100, the bank will say, well, but it's going to take you 10 years or so before you can come online, and your competition can find and lift the oil for $15 a barrel. They're going to undercut you tomorrow. Sorry. More than the capital cost, I think for some of the technologies, it's the energy cost that's the ultimate limit that I'm concerned about. If what we are doing is really wanting to add to the total energy, total CMOs that we have to do, we have to look at how much energy do you have to invest to convert that. If I have to invest more than a barrel of oil to get a barrel of oil of energy equivalent, then it doesn't add. It may still be valuable, because that's what you do when you do coal to liquids or some of these other cases. Because if you value oil more than, because it's the only thing that will fly your planes today, it's the only thing that's effectively used in many applications, then you say, all right, I don't care about total energy, I'm more concerned about oil.
I'm wondering about power generation and the electrical grid and its real inability to store power. Are we losing significant amounts of energy by having to ramp up and down power production and shunt it around the country to wherever it might be used? And would power storage solve some of that inefficiency?
The short answer is yes, it would. How much do we lose? I have heard the estimates that I have seen are somewhere, it's not very large. It's about 8% or so is the loss due to transmission and things like that. It's not much more than that. But the fact that you have to install capacities to be able to meet those very high peak demands means that a lot of your investments are not working all the time. So you have some power that's base power that's working all the time, but then you have about, more than 70–80% of the power capacity is used for less than 20% of the time. Is that something? Am I right on that? Some bizarre number like that. Some very skewed curve at the end. You must have so much extra capacity. So smart grid will allow you to save on that quite a bit. You don't have to build new capacity and therefore make those investments. Because, finally the investments are, you make them, and you have to think about what else could I have done with that. So like the CO2 also, the question that relates back to it also. What is it? What's the cost of the opportunity? What did I not do? Did I not invest in mosquito nets? Did I not invest in antibiotics? Because those are the kinds of choices that we have to look at. We can say, all right, yes, we want to go with photovoltaics. Great. Go ahead. Yes, you will not have any CO2 emissions. But if that's what your resource was, you had the monetary resource and you invested in that, the question that you have to balance against is, what was it that I didn't do with that money? And I think we all value things differently. And that's why it needs a public debate and a public conversation about it. I don't want to end the conversation by calling names or attributing theirs to their motives. We all have motives. We all have different motives. And we all value things differently. And the thing is to express yourself. So, I mean, I've been asked sometimes to summarize, the elevator pitch or something. Three bullet points for this 300-page book. It would be: don't waste, be informed, get involved.
Okay, I think that's a good note to end on, so thank you.
Thank you very much. Thank you.